Okay, thank you for coming to our second lecture. Today we're going to talk about convexity and optimization. Most machine learning algorithms will be some kind of optimization. So there are things that work differently. We're going to look at them as well. But things like neural networks or linear regression or logistic regression and so on will employ some kind of optimization process. Today we're looking at the fundamentals of those. Normally, it will be that when we have convexity, we will be able to make strong statements about the optimization process. If we do not have a convex problem, then normally all bets are off. So this is a very important topic because it means that when you know your procedure is convex, you will have the same result every time, or you will have reliable results. While when the optimization procedure is not convex, it might be affected by randomness or by your starting values and so on, which are usually chosen randomly. So different people might be getting different results. We're going to start in a similar fashion as last time. We're going to have a few definitions and what they mean. And we will then go on with a very fundamental optimization problem, which will explain or which will illustrate how constraint optimization works with linear optimization. And finally, we're going to look at the concept of duality for convex problems, which allows you to transform a problem into an equivalent, but maybe more easily solvable problem. So we start with the definition of a convex set. The set S, which is a subset of the Rn, is convex. By definition, exactly if for all two elements in the set x and y, and for all real numbers lambda in the interval 0 to 1, we have the following property. This weighted sum of the two has to be in the set S as well. There's one way to rewrite that. So equivalently, you can write y plus lambda times x minus y has to be ns. So those two are equivalent. You can just, by rearranging the term, you will get this. Now, what does this mean? Let this be our set S. What happens when we choose lambda equals 0? What happens here? We will have 0 times x, plus 1 minus 0, which is 1 times y, so we basically just get y. What happens if we choose 1? Yeah, exactly. We get x plus 1 minus 1, which is 0, x plus 0 times y. So we get just x. And what happens if we choose lambda equals to 1/2? Yes, 1/2. We will get 1/2 times x plus 1 minus 1/2, which is 1/2, times y. So we get 1/2 times x plus 1/2 times y, or x plus y divided by 2. So we get the average of the two. So if we have our x here and our y here, for lambda equals 1, we get x. Lambda equals 0, we get y. lambda equals 1/2, we get the point in the middle. What do you think might happen if we choose lambda equals to 3/4? Yeah, we will get something over here. So basically, if we plug in all the values of y, we get all those points lying in between the two. And so convexity of a set means you can pick 2 points arbitrarily from the set, and all the points on the interconnecting line have to be in the set as well. So is the set S convex? What would you say? Is this set convex? If you pick any 2 points, you interconnect them, is the line contained in the set? Yeah, so every interconnecting line will be in the set, therefore the set is convex. Good. Now, what happens with this set? Let's call it M. Is this set convex? Yeah, if it falls in between the arc, then the line will be outside the set. So M is not convex, while S is convex. We can now extend this concept of a convex set to a convex function. And what we need for that is the so-called epigraph of a function. So we have a function that maps a subset of the Rn into the real numbers. So it takes a vector, maps it to a real number. Can be anything. The function can look in any way. And then the epigraph of f is defined as follows. The epigraph is another set that is defined as follows. We can take the values we put into the function, and we take a real number, so we add another dimension, another direction, and we demand that the values we can take are greater above the function value at this point. So if we have, let's make a simple example. This is our function f of x. Then the epigraph, what would that be? Where can somebody describe it? So the y, well, what would be an x here? Is it an arrow, or is it, what is it? Yeah, it's a real number. X would be any real number here that we could pick, and the y would be our second axis, our up and down direction, and we demand that the y has to be greater than the function value. The y has to be greater or equal than the function value in the tuples. So what we could pick, for example, if we fix x here, then f of x would have this value, and we could pick all the y's that are even greater than the function value. So what is contained in the set is basically all of this, right? Yeah, this is the epigraph. And now that we have the epigraph, we can call a function convex exactly if its epigraph is convex. Convex function. So a function is called convex if its epigraph is convex. One very useful class of functions is a very simple looking kind of function, and there are things like lines, so linear functions or an affine linear function. They are all convex. So everything that looks like this is obviously convex. So every half space, if you remember from the last lecture, is a convex set. And that means every function which graph is a hyperplane will be a convex function. This property is quite important if you want to do minimization. So let's look at the definitions, at the fundamental concepts that we need for optimization. When we do now the definitions, we will usually speak in terms of minimization. Maximization is pretty much the same thing. However, usually we just have to switch the sign of the function. So if you want to minimize the function f of x, we can instead also maximize the function minus f of x. So in this sense, minimization and maximization are pretty much the same thing. However, to keep it easily writable so that I don't have to write it twice, we will just focus on minimization. So we again have a function f that maps a subset of the Rn into R. And an x, an element of the set S, is called a local minimal point. Exactly if So a value or a point x is a local minimum point if there's some epsilon greater than 0, it's a real number, epsilon, such that for all y in the set which are closer to x than epsilon, so the distance between the two is smaller or equal to epsilon, and then they will have an equal or greater function value. So basically, what we did here is we put the notion of neighborhood, like of proximity, of locality, into the definition by saying there is some radius, some distance that is really greater than 0, and everything that is closer to x than this distance, so which is in this neighborhood, will have a function value greater or equal that of f of x. So this is just a formalization of a concept that you, I'm pretty sure, definitely know. So if you have your function that might look like that, our f of x looks like that, then we would have a local minimum point here and here and here, because we can find a neighborhood for each of these where they have a smaller function value than everybody in the neighborhood, right? So we could, for example, pick the neighborhood here, this big, and everything that we look at just in this part will have a function value greater or equal to that one. Same thing happens here and so on. However, it's not a global optimum. It is really local because this function value here is still smaller than what we got here. Excuse me? Exactly, yeah. A function where we don't know anything about it can have many, infinitely many local minimum points. Like think of the sine of x and the cosine, which have the waveform, right? They will have infinitely many local minima. However, there are functions that have no local minimum or no minimum at all. Things that look like this. So they get smaller and smaller, they get closer and closer to 0. However, they never reach it. And there's no local minimum, because if you just go a little bit to the right, if you increase the value of x a little bit, you will find a function value that is even smaller. And as you said, as you suggested, we can now extend this concept to global minimum. which the definition is pretty much what we would expect. So everything we can put in the function will have a function value greater or equal to the global minimum point. For the sign, every local minimum point will also be a global minimum point. However, for this function, not every local minimum point is a global minimum point. Again, there might be functions which have local minima, but no global minimum. So, for example, this thing could just have like some mode here, and it would have, if it looks like that, like it could look like that too, right? And then we would have a local minimum here, but still no global minimum. However, and now this is where convexity comes into play. If the function f is convex, then we have a guarantee that every local minimum point is also a global minimum point. The proof of that is quite easy. You can do it yourself. I actually highly encourage you to do the proof. The idea for the proof, the intuition behind the proof is the following. If you had a function that has where the statement does not hold, so you have a local minimum, but you assume it's not a global minimum, which would tell you basically there's a different function value outside the neighborhood that is even smaller. Then what you can do, so this would be your local, and that might be global or just some function value that is even smaller. Then you could connect them. And the connecting line cannot be in the epigraph anymore. So you know this function cannot be convex. If basically what you prove, if a local minimum is not a global minimum, then the function cannot be convex, which is the same thing as saying if the function is convex, then the local minimum will be the global minimum. So basically when you do the proof, literally what you have to do is find, using the expression that we looked at, quite exactly similar for convexity, and then plugging in the definitions, and you will get the contradiction. Another theorem that is equally easy to prove is the following. And it relates differentiability, a function being differentiable, so you can calculate the derivative. It links this to minimal points or extremal points. So what we have here, if the function is differentiable, which is actually necessary for that, then we know if we have a local minimum point, then the differential at this point will be 0, which is again something that you might know from school, where when you had to optimize a function, what you did was maybe setting the derivative to 0. When you have a parabola here at the minimal point, the derivative is 0, right? This is what you already knew, maybe. In the homework, you will prove that this theorem holds true. The proof will be guided, so it's not like that you have to come up with the whole idea all by yourself, but instead the proof is broken down into several steps, and you can just go step by step. If you cannot do one step, this is not that bad for you, because you can just skip it and do another step in the proof. So to really give you an understanding of why things work like that, as I always say, you really have to do the homework. There's no way around that, sadly. It will give you an insight of how and why things behave like they do. And maybe even more important, it will train you in the way of thinking logically. Like, it will give you experience in proving things, which is a very, very important skill. So especially if you want to dive a little bit, or even if you don't want to, but you have to dive into the realms of mathematics, then doing proofs is the best way to proceed there. There are, if you want to learn about these things, there are very good videos on YouTube, of course. What maybe comes into my mind the most is a YouTube channel that is called 3 Blue, 1 Brown. And that guy does really good videos, like extremely good. However, there's one drawback, so you cannot rely on these things alone. If you think about the task, or if you think about understanding something as climbing a hill, then there are two ways to get on a hill. You can pay somebody, or you can have somebody who puts you on his bike and he drives you up the hill. And then you're up on the hill and you can see everything that is down below, right? You have the nice view, and that is very cool. But the moment you have to get on a hill yourself, it will be very difficult. However, if you're used to climbing all the hills yourself, when you encounter a hill, you will just hike up as if it was nothing. So 3 Blue, 1 Brown is a master in carrying people up on a hill. It's extremely good. It's very good. However, it is not possible to substitute your ability to understand something on your own, which you have to. There's no way around it because sadly he cannot make a video on every single topic that exists, right? So really do the homework and get all the experience and all the stamina in climbing hills that you need. Okay. Ah yeah, and having this allows a corollary, which is a simple conclusion. If F is convex, and the differential at x is 0, then you know that x is a global minimal point. So that means if you have a convex function, what you need to do, and the function is differentiable, if you want to optimize, all you have to do is finding a point where the derivative is 0. So if you can find equations, which is what we did for the linear regression, if you find equations that you have to solve in order to find a point with derivative 0, then this is all you need to do. Solve these equations, and then you have optimized, and then you have solved the optimization problem. Oh, and what we also need, or what might come in very handy if you want to prove that a function is convex, is that if a function is twice differentiable and the second derivative is, which will give you a matrix, a symmetric square matrix, and this matrix is positive semi-definite for all x values, then the function will be convex, which is also maybe something that you did in school. If you've seen the concept of convexity before in school, what you might have seen is that you had to calculate the second derivative. If it was positive or non-negative for all values, then you knew the function is convex. So what I'm doing here is I use the greater or equal to 0 quite liberally. So what we mean here is that this will be a matrix, and the matrix has to be positive, semi-definite. Then we say it's greater or equal than 0. So because normally, how would you compare a matrix with many values to 0? So this is not what we mean. What we're talking about is we say that it's positive semi-definite. And as an example for that, you might remember quadratic function, which will have a linear derivative, which is 0 at the minimum or the maximum. And the second derivative will then be a constant. And if your parabola is opened, is opening to the upside, then the second derivative, this number will be positive. If it was opened downwards, then it will be negative. So this is also, this is a simple example of the theorem. The criterion that the second derivative has to be positive semi-definite is one criterion how you can prove that a function is convex. In the homework, you will prove quite a few more rules, which might help you when you have a problem at hand to prove that the function is convex. And so again, even if you don't actually solve the homework, it might be worth to at least look at it so that you know about those tricks. In practice, now you might wonder, why do I even have to bother with those things if you have a problem that is very specific and where you really tailor the solution yourself, then you might have a very unusual function that you have to optimize in order to train your model. So what you would do is, what you might be doing is to come up with a model that has very special properties and so on. And you want to know when you train it, can I train it reliably, or will the results be subject to luck? So, and for that you might want to know if your error function or the function that you optimize for training the model is actually convex or not. And for that, you can employ those rules. So let's look at one very general and very important case of optimization. That is linear programming. In the modern sense of the word programming is a misnomer here. People, like the concept of linear programming is quite old now, like, yeah, it's getting 100 years old. And people back then would call a decision rule or a policy also programming, and this is where the term comes from. So when you read quadratic programming or linear programming, or maybe also mixed integer programming or problem, then what people actually mean is optimization problem. You can substitute the word program or programming for optimization with optimization problem. A linear program has this form. You want to minimize over x in Rn. A linear function, so we have a vector c, and we make the scalar product with our vector x. And we have the following constraints. So st means subject to the following constraints. The matrix vector product has to be smaller or equal to some given vector, and that is meant element-wise. So it means that when you multiply a matrix with a vector, you get another vector, right? And every element of that vector has to be smaller or equal than the corresponding element in B. So what you get in the end, matrix vector product, as we said, you can think of it as a bunch of scalar products. And every scalar product has to be smaller or equal to the value in B. And that is just the same thing as a half space, if you remember. So what you say here, what you demand here, is that the x's that are allowed are all are in the intersection of many half spaces. And we're calling this problem a linear program or a linear optimization problem because everything we have here is linear. So the cost function is linear, but also every constraint is a linear constraint. And you can, in this case, you can also incorporate equality constraints because you can say the scalar product has to be smaller or equal than B. And you can also demand that the same scalar product has to be greater or equal than B, which is the same thing as multiplying both sides by -1, right? And you say it's smaller or equal and greater or equal, which results in it has to be equal. So how does the set, we call it a feasible set, everything that is allowed, how does it look like? So we just have to think about half spaces. Let's look at a two-dimensional case. If we cut off one half space, means we do away with all of this. The next half space might cut away with all of this. We can cut away all of this, cut away all of this, and what we end up with would then look like that. And the intersection of a bunch of half spaces is what we call a polyhedron. And you can show, you will show in the homework actually, that the intersection of convex sets is another convex set. So because we know that half spaces are convex sets, we know that the polyhedron, which is the intersection of half spaces, will also be a convex set. So we have a convex optimization problem here, or what we call a convex optimization problem. The feasible set is convex, as we've just argued, and also we have a linear function here, which is also convex. So everything in our problem is a convex function. And we can rewrite that equivalently. This is the same thing as saying x minus b is smaller or equal to 0. So if we want to solve a linear optimization problem, we cannot simply set the gradient to 0, right, of our objective function, because it will never be. The gradient is equal to c at all points, and that will never get 0 in any optimization problem that is of interest. So we have to extend the concept a little bit. So we instead of setting just the gradient to 0, we want to set this whole sum to 0. And now what do we mean? Like f of x would be defined as c transpose x, and c of x now maps from Rn to the Rm, and x is mapped to ax minus b. So we say, instead of saying ax minus b is smaller or equal to 0, we could say g of x is smaller or equal to 0. And why should we be interested in points that look like that? So I just try to redraw our polyhedron here, our feasible set. And the components of G, so G consists out of m different functions, right? And every side here of the polyhedron, every edge corresponds to one of the components of G. And they all have gradients that point outward, which is the normal vector of this half space, or of this hyperplane that gives you the half space. And they might have completely different lengths. Nobody really knows, so it depends on the whole problem. And your gradient from the function f, the c, might point in this direction. So when you want to solve the linear optimization problem, what you want to do is you want to go, because we minimize, we want to go as far as possible in the opposite direction of C, while still staying in this polyhedron. So, for example, when we are up here, what we could do is we could go down, 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 down against the direction of C. So you can also think about the problem just of turning the polyhedron such that C points upwards, and then you want to find the bottommost corner. So you can think of linear optimization as building a polyhedron, then turning it, and then finding the bottommost corner, or the bottommost part of the polyhedron. So when we are here, what we could do is we could go down until we hit this wall, and then, well, we can still go down, we follow the wall until we're here in this corner. And what we say with this equation here is that we can express the gradient, we can express the direction C in terms of gradients of the functions that make up G, which means we can kind of catch the gradient. So when we hit this wall, we cannot find a solution to this equation here, because the gradient of f, because C is not in the span, if you remember from last time, the span is not in the span of this gradient. However, when you go further down to the corner, then it is in the span, when you take that gradient as well. And another thing, which is very important, is we have to pick the multipliers to be greater or equal than 0, because otherwise the upper corner would also give you a solution. So another way to really think about it very visually is maybe I have to go, or C would be pointing in this direction, and which means I want to go down here. And there's here is like a wall. So when I want to walk this way, at some point I will run into the wall. I can't go on anymore. However, this still pulls me that way until I hit another wall here. And then the gravity, if you want to call it, or if you think about it like that, is basically, or the force that pulls me downward can be catched by the walls. Otherwise, I would still slide, right? And this concept is formalized with an equation like that. And there's one more important condition. So we want that, we demand that the lambda is greater or equal to 0, we demand that this equation is true, but there's one thing missing, because what could also happen is that you're inside the set. This is not yet, that you didn't hit any wall. You could still find a solution here, but you're still not at the optimum. So there's another condition that we have, that we need to find the optimum, and that is that lambda transpose g of x, so here we have the gradient, here we have the function, is equal to 0. And because the lambda are greater or equal to 0, what we get here, and this condition here tells us, also fixes the sign of all the components of G. So this corresponds then to this. And what this enforces is that the case that we're somewhere inside of the set is ruled out, because G, this component of G won't be 0. So we're not allowed to take it as a multiplier, to take its gradient into the equation. However, when we touch the wall, this component of G becomes 0, and then we're allowed to take it with a multiplier. Otherwise, we would say it's not possible to take that into account. So if you think about the example or the analogy with the walls, we make sure that you actually have to run into the wall. The distance to the wall has to be 0 in order for the wall to stop you. Yeah, and at a junction, basically, it holds for all walls. We say a wall only stops me if I actually run into it. This is what it means, yeah. So at a junction, in order for the next wall to stop you, what it means is, well, you have to touch that wall as well. Only then can it stop you, otherwise you can still walk. So if you want to solve a problem like that, you have to find a point that fulfills those 3 demands. Now, why is linear programming such a good and such a general example of constraint optimization? So when you think about any differentiable function, differentiable means when you're in a very tiny neighborhood of a point, or there is a neighborhood of any point, where the function almost looks as if it was linear. So when you're in the neighborhood of a local minimum, you can basically approximate every function that is in play with its derivative. And all of a sudden you get something that looks like a linear program. So when you want conditions on the optimization of a convex function with convex constraints, at any local minimum point, it will behave like a linear program under some mild assumptions. And that means those conditions actually hold, like the way we formulated it here, the way we wrote it down, actually hold for a very general case. It's not just for linear optimization, but it holds true for most kinds of constraint optimization that we will encounter. So with this as a fundamental, as the fundament of constraint optimization, maybe we should illustrate that here. So we have our vector C. And we want to catch it with those gradients. And we add them up and we want to get to 0. So basically what we geometrically do, take the negative of C, and here we can find positive multipliers for this gradient and also for this gradient. And we get 0 if we add it with C. So with linear optimization as the fundament, we can now explore the concept of convex duality, which is the last thing we're going to look at today, and which will give you very sound foundation in optimization in general. Convex duality is a thing of convex optimization. Convex optimization means the objective function we want to minimize, as well as all the constraints that we have, are convex. So we have 3 functions, which are all convex functions. Then we call the primal problem the minimization of f of x subject to the constraint that g of x has to be smaller or equal than 0. And h of x has to be equal to 0. So f maps from Rn into R. G maps from Rn into Rm, and H maps also from Rn into, let's say, R L. So M is the number of inequality constraints that we have. L would be the number of equality constraints. And for our problem, we can define the so-called Lagrange function, and we also demand that they are convex. Differentiable. So they're convex and differentiable. Then we can define the Lagrange function. F of x plus lambda transpose g of x plus mu transpose h of x. So this function now has a few properties. It will be convex in X because every function here is convex in X, and you can see in your homework, or this is even equal to 0. We will prove that in your homework. And it is convex and concave in mu and lambda. So because it's linear in lambda and mu. Did you copy all of it? Okay. Yeah. It is even concave. Concave is kind of the same thing as convex. Oh yeah, sorry, I didn't explain that. But flipped. So a function is concave if a function f is concave if minus f is convex. So basically you flip it. You mirror on the y-axis, and then it's the same thing as convexity, but from below. So we were always talking about minimization problems, and that the function needs to be convex. If you had a maximization problem, the same thing would hold if the function was concave. So in this sense, everything is the same as long as you just mirror it. So we make another assumption, and that is that there is a minimal point. So there are convex functions, as we said, that do not have a minimal point. However, we assume that there is one. And we define x hat of lambda and mu. So because we have a convex function and we assume that there is some minimum, we can pick that with respect to lambda. Like we optimize over x and assume that lambda and mu are fixed. So if I give you a lambda and a mu, because those two are fixed and the whole function, the Lagrange function, is convex in x, you were able to optimize, or you would be able to optimize the Lagrange function and find the corresponding x that minimizes the Lagrange function for the lambda and mu that I gave you. And you can just basically put this into a new function. So somebody gives you the lambda and mu, and the function will return the minimal point that minimizes the Lagrange function with respect to this lambda and mu. So in practice, how do you get it, or how would you arrive at this minimal point? In practice, because the functions, you want to pick the functions in a way that you can optimize them, normally by saying, because they are differentiable, you will use that. So you will end up with equations that say you have to set the derivative to 0 of the Lagrange function. and that gives you a bunch of equations. So in practice, you use the equations given by the differential with respect to x. Has to be equal to 0. And with that, we can define the dual Lagrange function. Which we get by just plugging in the minimal point with respect to x that depends on the lambda and mu. So basically we eliminated our variable x here. And now this function only depends on the multipliers, on the so-called Lagrange multipliers, lambda and mu. And with the dual Lagrangian, with the dual Lagrange function, we can define the dual problem. So we want to maximize the dual Lagrange function with one constraint that we had. The lambda has to be greater or equal than 0. So why do we call it a dual problem? It turns out that solving the two problems is equivalent. So when you solve one of the problems, when you have solved the primal problem, you can also solve the dual problem. When you solve the dual problem, you also solve the primal problem. But it is not the same thing, right? Because the variables x are now gone. When you solve this problem, x is not existent anymore. Now this only depends on your constraints. So this is a very interesting way of thinking about it. When you have a completely convex problem, it turns out that solving it can be done completely in terms of the constraints that you have. So much so that the initial input space, the initial space on which you define the problem, doesn't even matter anymore. So when you have a problem with linear optimization, right, this would be something that has a dual problem. We will look at that like as an example shortly. But just conceptually at first, when you think about it, you have a convex objective function, it's differentiable, convex constraints, also differentiable. Therefore, you can define the dual problem under some mild assumptions. Or no, actually always. You can get the dual problem, and now it does not depend on x anymore, but only on the constraints you have. So what happens, what would you do if A looked like that? An extremely broad, but not very high matrix. What would you rather do? Would you rather solve the primal problem, or would you rather solve the dual problem? How many dimensions do you have to optimize over when you solve the primal problem? Like, let's say this is n and this is m. x would live in Rn, right? So you have n, which is extremely huge number. So m is way smaller than n. You would have extremely many dimensions that you have to take care of. However, when you construct the dual problem, how many dimensions will you have for the dual problem? It's just m, because it now is formulated in terms of the constraints you have. So what was before a problem that had extremely many dimensions to take into account, in the dual formulation becomes a problem that only has very little dimensions to take care of. It turns out that what might happen is that the primal problem is infinite dimensional. You can have an optimization problem over infinitely many variables. However, if you only have a finite number of constraints and the problem is convex, you can still make the dual, and all of a sudden you turn an infinite dimensional optimization problem into a finite dimensional optimization problem. So this trick, we will look at that. There are things that are called kernel methods. It's called kernel method, which basically employs exactly this trick. So it gives additional power, if you want to say so, to your machine learning technique by employing infinitely, or in some versions, infinitely many dimensions. But but you're still able to solve the problem because it has a dual that is finite dimensional. If we assume that we can optimize the function, the Lagrange function with respect to x, that it has an actual minimal point, which is not the case as we learned for all convex functions, then we can do the following trick. We can define x hat of lambda and mu as some minimal point with respect to x of our Lagrange function where we here consider lambda and mu pretty much to be fixed. So we can express for a fixed lambda and a fixed mu the minimal point x hat of the Lagrange function. In practice, what does it mean? In practice, it usually means that you would set the derivative. In practice, you would set the derivative of the Lagrange function with respect to x to 0. And because the function is convex, you would get your optimum. So you desire it to be 0, and from this equation you derive an expression for x hat. With that, now we can define the dual Lagrangian function. And the dual Lagrange function is nothing but the original Lagrange function where we put in our expression for x hat, which basically eliminates x as a variable, and the dual Lagrangian function now only exists as a function of lambda and mu out of those two variables. And with this, we can define the dual problem of our primal problem. So the lambda greater or equal than 0 comes from the fact that we have chosen them to be the Lagrangian multipliers for our optimization problem. And we further want or demand that this must fulfill this equation and this equation. So we want that this is the actual minimum of the Lagrange function with respect to x given lambda and mu. So what does that mean in practice? In practice it means, again, you have to optimize this subject to this and subject to this. So let's do an example for that. By the way, so one can show that under some assumptions that we already made, that the optimal value of the dual problem, so the maximum of this function with those constraints, and the minimum of the primal problem under the primal constraints have the same value. And one can further show that the dual problem will be always below, like have a lower value than any of the feasible primal solutions. So if you plug in any feasible combination of x, lambda, and mu, like x's that fulfill all the constraints set on the primal problem, the function value that you will get will be greater or equal to any feasible solution that you get from this function. So this is a lower bound on our primal problem. So let's derive the dual problem as an example for linear programming, for linear program. So our primal problem is minimizing C transpose X subject to, and now we make a little change so that we can get it in the form that we assumed for the primal problem. Subject to AX minus B must be smaller or equal than 0. Okay. Now, how would the Lagrange look like? The Lagrange function will be C transpose X plus lambda transpose AX minus B. Okay. And when we now set the derivative with respect to X to 0, what do we get? We get this equation. And now if we plug in that, we get for L hat this minus lambda transpose B. So basically what we did is we substituted lambda transpose A with minus C and plugged that in here. So the dual problem will be maximizing minus lambda transpose B over lambda, subject to lambda greater or equal than 0, and A transpose lambda must be equal to C. Oh, excuse me, minus C, which is this equation. So this would be our dual problem now. And here we can see something that is where we can illustrate why we do this usually. Why would one ever even transform the primal problem into the dual problem? And the reason here is simple. Before that, we had the problem was formulated in terms of x. So if our A is looking like this, where we have n columns and m rows, and m is way smaller than n, we have a lot of variables here, like many variables, and we can transform that here into a problem that now only has m variables. So before x was living in Rn, we had n variables. The dual problem, however, because we eliminated x, now the constrained matrix looks like that. And while x looked like that here, so many dimensions, many variables, lambda only looks like this. So we transformed a very high dimensional problem into a lower dimensional problem. Before, it was scaling in the number of variables. The primal problem scales in the number of variables. The dual problem, however, scales in the number of constraints. So if one has less constraints than one has variables, it might be a wise consideration to think about the dual problem. Finally, let's look at a few optimization methods. In the end, in practice, somehow you have to solve the optimization problem the model you have yields. So there must be some mean, or you need some mean to solve the actual problem. And there are a few approaches, especially things become a little bit more feasible if you can differentiate the function you want to optimize, because then you can do something that is called gradient descent. Where one employs a simple update rule. So if you have your value of xk right now, and you want to calculate the next x in your iteration, what you do, as a reminder, you want to minimize the function. We take our current x and we subtract from it some positive alpha k. So we might choose that number. it is what we call the step size times the gradient with respect to x of f of xk. So what does it mean? You can imagine the problem, an optimization problem, where you don't know anything about the function, but its derivative and its current function value. You can imagine it as being in midst of some mountain range, and you can't see anything. So seeing some other place actually corresponds to knowing how high it is. However, for a function, you normally never know how high it is, except if you evaluate the function at this given point. So you would need to calculate all the values, which you cannot do normally. So all you can do is you can calculate how high am I right now, and you can, by calculating the derivative, you know the slope of the surface that you're currently standing on. So you don't know anything how the landscape actually looks like, but what you know is this direction points upwards and this direction points downwards. So when you want to descend, when you want to optimize the function, which in our example means that we want to go downhill into the valley, what you do is you find out in this mist where you can't see anything, you find out in which direction you go down, and you just take a step downwards. That's it, pretty much. So there are obvious problems if you don't know anything about the function. If it's not convex, then things might happen, like you go down for a while, and all of a sudden, the problem is that you can't go down anymore because you're in some kind of sink. However, you're far away from the valley. You're still very high up. This cannot happen with a convex function, as we've seen in the first part of the lecture. So a convex function gives you the guarantee, in some sense, under mild assumptions, that just by doing gradient descent, you can definitely go to the minimum, to the global minimum, into the valley where you want to reach. And there's no way of getting stuck in a sink high up in the mountains. The question also is, how would you choose the step size? So there are many ways of doing it. There are ways with which you can easily guarantee that you will go down at least a little bit. What you can do is something like you pick one. If you do the iteration, if the step size was too high, that means you did not go down because you jumped over the valley. Then you just go back, you divide the step size by, let's say 2. So you cut it in half, you do the same thing, and you do it over and over until you actually verify that you went down a little bit. In practice, this is usually a little bit unfeasible, and one has to come up with a clever way of choosing it. That sometimes means just trying. So when you optimize the neural network, what you will usually do is that you have to try many different step sizes, and you never know. For a problem that looks like linear regression, you can actually calculate the optimal step size, which you can look up in the internet, and we're not going to go into this topic here, but you can calculate it and guarantee that you will go down as fast as possible. There are several versions of gradient descent, like accelerated gradient descent, which will give you better guarantees for a convex function on how fast you will descend. And usually, what it comes down to, if you don't know anything, you will have to resort to this method. Another illustration, to bring that down to our one-dimensional functions. If this is how our functions look like, and we are currently here at xk, we calculate the gradient, which points upwards here, and we just go down the other way. So let's say if you have huge alpha, we have here alpha times the gradient at xk. And here the gradient at xk. And our next iteration, iterate, would then be here, xk plus 1. And you might already see, if you do that, you go down and down and down, and the gradient gets smaller and smaller and smaller and smaller because you approach the minimum, and at the minimum the gradient is 0. And this is how you approach the valley. Another way that we have used for the linear regression problem is solving this equation, setting the derivative to 0 and solving for the x value. So there are different advantages and drawbacks, right? If you remember, for linear regression, what that meant was we had to solve a system of linear equations. That means the problem scales in the number of dimensions that we have. So if you have, actually it scales with the cube, usually, of the number of dimensions. So if you have a linear regression problem with twice as many variables, you would usually have to do 8 times as much work. However, after solving it, you're immediately done, which is something in and of itself, right? Because that might take a while, and you don't know. However, there's kind of a trade-off, right? So you can decide for gradient descent, which will scale in the in the actual difficulty of the problem. Gradient descent will fit very well if you want to optimize a function that looks like that. That is pretty much regular. So we have our optimum here, and our start might be here, and calculating the gradients will bring us immediately, very quickly, if we optimize over the step size actually in pretty much one step, it will bring us to the optimum, and we wouldn't have to work anyways, at all. We wouldn't have to work at all. If we solve the equations, we would still need to do the whole work. But how does it look like if we have an error function, an objective function that looks like that? Now the situation is very different, because when we are here, so our optimum would be down here, but the gradient points us this way. And if you go a little bit too far, we have to go this way again. And then we have to go this way. And it will take ages to arrive at the optimum. In this case, it might be better to solve the equations, the system of equations. The last method that I want to discuss, because it has so many applications, and it's interesting to understand how the Lagrange multipliers work, is what we call an active set method that we would use for constrained optimization. For linear programming, this is pretty much what is known as the simplex algorithm. So for constrained optimization, we can use something that we call the active set method, where we basically ask ourselves the question, which inequalities, which of the walls are binding for us, which of those walls hold us back from the optimum. So the way to illustrate this is by going back to our case for linear optimization. So we assume that we will have some linear inequalities as constraints. And I will draw in the gradients. And our objective function, the gradient, C. Let's make it a little bit shorter. So, fine. So what we do is we start somewhere in the feasible region, somewhere in our polyhedron, and we then just go until we're held back by walls in some way. So what could happen is that we actually start out over here. And we will employ, now here we're hit by two walls. So the walls would hold us back. We couldn't move, we're in the corner. If we consider both of the walls to be in the active set. So the active set means the inequalities that are necessary or that are binding at the optimum. So the way to find out if we now could let go of one of those walls is by using this equation that nabla f of x, the gradient, plus the derivative of g times lambda must be 0, or that means in our case minus c is equal to minus c is equal to this linear equation. And if you look at it like that, it gives you a linear system for lambda. So if you solve this linear system, you get the lambdas. And we can do that graphically too, like we can do that by solving this system of linear equations. If this is minus c, and we have our two gradients here, that one and that one, we can see how do we have to express minus c with those two gradients. And it turns out that what we have to add here are both negative, right? So we have to go against the direction of this gradient, and we have to go against the direction of the red gradient. Now, we know from our considerations about linear programming that in the optimum, all the Lagrange multipliers, those lambdas, they have to be positive, because otherwise the wall is actually on our back. And with that, we can figure out what the sign, by solving this system of linear equations, we can figure out what the sign of each component of lambda is. And we can thus decide which lambdas we don't actually need, which walls we could let go of. And when we have multiple walls we could let go of, which is the case in this setup, then what we can do is just finding the one with the most negative value and let go of this wall, which would be, I think, the green one here. And we can then let go of this wall and go along the other wall as far down as we can until we hit the next wall, which would then be this corner. So we went from here to here. And we can just do the game again. We can, again, solve the system of linear equations. The but this time we see that only one of the multipliers is negative, and that is the one for this wall. So we let go of this wall, we go down. We go down again to this corner. We can do the game again, calculating our Lagrange multipliers. And finding that both of them are positive, and now we know that we are actually at the optimum. So this way of going along the edges is also called the simplex method. It's a version of the active set method where you basically really go along the corner, because what we could have done is we could let go of both of them at the same time and go down immediately, like follow the gradient until we hit this wall. Or if it was a quadratic optimization problem, the optimum might be in here, and we would again just let go of those inequalities. So the idea of the active set method is just to figure out locally which inequalities are necessary and which are unnecessary, and then letting go of the ones which are unnecessary and keeping the ones that are necessary. The last thing that I want to mention in the context of optimization is the stochastic gradient descent, which is a version of gradient descent that is specialized for a certain kind of objective function, and you do it for objective functions that look like this. You have a sum of several functions which are all kind of similar. This is the case in machine learning, where when you have a billion examples of chairs, the chairs are all kind of similar. And instead of calculating the gradient on the whole sum, what one does, so normal gradient descent would be xk plus 1 is xk minus alpha k times the gradient at xk. However, to calculate that, you would need to differentiate, if n is very large, for a billion chairs, you would need to differentiate the error function for all of the billion chairs, which is a lot of work. So what people do instead is they say at each iteration, so this is was the normal, and for the stochastic variant, at each iteration, one only uses a subsample or even a single sample. Of those single functions. So what you could do is you calculate the error on the image of one chair, calculate the gradient from that one chair and then immediately do a step. And this way you can incorporate the information way more efficiently, way more efficiently actually, than you could do if you calculated the gradient for the complete sum. However, the convergence behavior close to the optimum is of course not that good because you don't know, you cannot take the entirety of chairs into account. With the stochastic variant, you always only use one chair, and effects that might cancel out in the complete picture will persist in that setup, and convergence does not happen the same way. However, in practice, this is the biggest component actually of deep learning from the last years that made it feasible. It is stochastic gradient descent because it allows to incorporate vast amounts of data that would previously have been infeasible to incorporate. So thank you very much for joining the lecture. I hope you do the homework regarding this because it will teach you a lot about all those things that we were talking about. And I'm looking forward to see you next time. Thank you very much.